3U, this is our quadratics lesson 4, and I just like to start with a warm-up question. We can solve problems that ask for maximum and minimum values of things, which can be very helpful, by finding the vertex. The vertex always gives us that upper or lower limit. So we're going to do just a short one. Find the minimum product of two numbers whose difference is 8. So I'm going to call my number 1 n for lack of creativity. Let n be first number. Okay. The second number has to be different than the first one by 8. So if their difference is 8, I could then say that my second number is n minus 8. I want to find the minimum product. So I want an equation about product. So product, in terms of these numbers, would be n times n minus 8. And I want the minimum product. The form I have it right now is in factored form. I can find my two n-intercepts. They're 0, 0, and 8, 0. So I know that my vertex, n-intercepts, I know that my vertex will lie on 4 something. So I can find my vertex that way quite easily. Another way that I can find my vertex is to expand this and put it in vertex form. Either one would be fine. So expanding it, it's like that. That would be in general form. In vertex form, I can complete the square. Skip a line. My goal is that. In order to have that, I need to add and subtract whatever 4 squared is, minus 4 squared is, to line 2. There we go. Those 3 things give me my goal of n minus 4 squared, and I'm left with those leftovers. So from the first form, I can find my vertex. I haven't quite finished yet, but I could. Or from this form, I can find my vertex is exactly 4 minus 16. If I have a quadratic that opens upwards with a vertex of 4 minus 16, my minimum value, in this case it's a minimum product because that's what my function is, my minimum product is minus 16, occurring when n equals 4. So we can use the vertex, however we get to it, to find minimums and maximums. Today, our goal, actually over the next couple of days, is to get to the right page, is to get to solving things for x-intercepts by using the different forms. Today has a means to an end. We're going to practice using roots, radicals, square roots, and so on, so that by tomorrow and the next day we can use square roots to answer questions about x-intercepts, or roots, or solutions, however we word that. So today is operations with radicals. A radical is a root. Square root, cubed root, and so on can be higher order. A mixed radical has a coefficient other than 1. For example, 2 root 3 would be a mixed radical. Has coefficient other than 1. An entire radical is when there is a coefficient of 1, invisible perhaps. So root 125 is an entire radical. Like radicals are as they sound, look similar. For instance, 2 root 6 and 7 root 6 would be like radicals. It's kind of like a common denominator in our thinking. Let's do some examples together. If you'd be patient with these and assume that the top of the root sign does extend. There we go. And also, there is no number in the root sign. We will assume that it's always a square root unless indicated otherwise. Square root of 4 is 2 because we can have two identical factors under the root sign. By taking one out, you have found the root of 4. Root of 100. Likewise, because it can be written by two identical factors, square root is saying find one of them, and you have your answer. Square root of 24 is not quite so pretty. Square root of 24, and I'm going to write it as fully factored as I can. 24 is 2 times 12. 12 would be 3 times 4, which would be another 2 times 2. Let's do a quick check. 2 times 3 is 6, times 2 is 12, times 2 is 24. So I have it fully factored. If there are two identical factors, I can take one out of the root sign. So I am left with 6 inside, but because I had two identical 2's, I can take one outside of the root. 2 root 6 is the most simplified form for root 24. Root 72 is 36 times 2, which I could write as 6 root 2. 5 root 3. If I wanted to write it conversely as an entire radical, to put the 5 under the root sign, I would need 2 of them. In other words, I replaced a 5 with the root of 25, which we know to be true, times 3, because we already had a 3 under the root. As an entire radical, we would write that as root 75. 4 root 5. 4 as a radical would be 16, and I already had a 5. To write that as an entire radical, I would have root 80. Root 5 times root 11. Root 5 times root 11, I'm just going to write as approximate decimals. I'm going to try and write as approximate decimals. There we are. Root 5, according to my calculator, is approximately 2.24. And root 11 is approximately 3.32. When I type in root 5 times root 11, and I'm typing it all over again so it's less rounding errors, 7.42. Interestingly, if I type in root 55 into my calculator, 55, oops, my calculator doesn't like that, I get 7.42. So, from one example only, and the fact that you trust me implicitly, when we multiply radicals, we can write them separately as root 8 times root 2, or put them together as root 16. Root 16 is a beautiful number. It's 4. Root 8 and root 2 are both not so pretty, but if you were to multiply them together, you would get a lovely. Sometimes this can be helpful. Negative 4 root 6 times 2 root 6 can be done in a number of different ways. I would be tempted to write entire radicals for both of them. Negative 4 root 6, I have my 16 now under the root sign, the 6 that I already had. The second one, I would put a 4 under the root sign to replace the 2 times the 6 that I already had. I know that I can put all of that under one root sign for multiplication. So 16 times 6 times 4 times 6 is the square root of 2,304, which is kind of ugly and hard to know what factors it has. There are other things we could do with this. We could instead leave the minus 4 out, put it with the 2, put the two sixes together. I can do those in any order, so I can put the 2 together under the root sign, which would give me root 36. So I've got a whole number 4, a whole number 2, and the root of 36 is 6. Final answer would be minus 48. Is it true that the square root of 2,304, I can't do two things at once, sorry, is 48? Yes, it is. So order of operations is the same for multiplication, and we just have that one little trick that we can put the roots together under the root sign and make things a lot easier. The last one on this page is minus the root of 21 times minus 2 times the root of 14. I noticed that 21 and 14 are related. 21 is 7 times 3, and 14 is 7 times 2. So those 7s could go nicely together. I'm going to put all of the radical parts together. So under my radical, I have two identical 7s. So I can take a 7 out. I'm still left with 6 under the root sign, and there's nothing pretty about that. But I have my minus 7, and everything's being multiplied. Minus 7 and a whole minus 2. I would have positive 14 times root 6. Best answer would be 14 root 6. It's not writing it as an approximate decimal. For addition, again, I'm going to use my calculator just to look at this. Root 5 added to root 3, I'm going to write as approximate decimals. Root 5 is 2.24 approximately, and root 3 is 1.73 approximately. So approximate answer is 3.97. Square root of 8, just going to see if adding works as well in the same way. Root 8 is 2.82. Not close at all. So for our adding rule, it's more similar to fractions. I can add 2 root 3 and 5 root 3 because they are the same. But I can't add root 5 and root 3 because they are different. 2 root 3 and 5 root 3 would add to 7 root 3. Let's just check that they are indeed the same thinking process. 2 root 3, 2 times the root of 3, according to my calculator, is about 3.46. And 5 root 3 is 8.66. So together, approximately 12.12. 7 root 3 is 12.12. So we are adding like radicals, just like we would add like terms in fractions. So for the next one, I want to simplify these as much as possible so I can find like terms in order to add. At this point, there are no like terms. So root 12. If I could simplify that, I would notice that 12 is 4 times 3. So I'm going to be able to write that as 2 root 3. Take one of the identical factors of 4 out of the radical. Root 18 is 9 times 2, and 9 has two identical factors of 3. So I can write it as 3 root 2. 27 is 9 times 3. Take an identical factor of 3 and leave a 3 under the root. Lastly, 50 is 25 times 2. I can take an identical factor of 5 out, left with root 2. Now I am adding root 3's and root 2's. For my root 3's, I have 2 of them, and minus 3 of them, I have minus 1 of them. You don't need the 1, it can be invisible. For my root 2's, I have 3 of them and 5 of them. I have 8 root 2. Final answer. Just like we would do a FOIL, the rules of radicals would apply the same, remembering how we deal with radicals when we multiply and when we add. So a FOIL for this one, firsts would be 1 times 2. Outside would be 1 times root 6. Inside would be minus root 3 times 2. We write it as a coefficient first, the root second. Lasts would be minus root 3 times root 6. If I can simplify any of that, I will. Root 6's and root 3's cannot be added. They're different. So far there's nothing that I can do. But I'm going to see what happens when I multiply root 3 times root 6. I am allowed to write as root 18. Root 18 can be simplified as 9 root 2. Sorry, 9 inside the radical gives us a 3 outside of the radical, 3 root 2. There are no common terms. Root 6's, root 3's, and root 2's are different. We can't add them. We are done. 2 root 5 minus 3 root 7 all squared, be careful, means 2 of them, 2 root 5, take away 3 root 7, times itself twice. There we are. We need to FOIL that. Firsts would be 2 root 5 times 2 root 5. The coefficients give me a 4. Root 5 times root 5 is root 25. There's my firsts. Outside is 2 root 5 times negative 3 root 7 will be a negative. The coefficients give me 6. Under the radical is 5 times 7, which is 35. Outsides, negative 3 root 7 times positive 2 root 5 is a negative. Coefficients give me 6. And under the radical, I have 35. Again, lasts. Negative 3 root 7 times negative 3 root 7 is positive 9. And under the radical, 49. We can simplify that. Root 25 is the same as 5. Root 35, we can't make any more simple. The factors of 35 are 5 and 7. No identical factors. That's as good as it gets. We happen to have, however, 2 piles of them, so we can at least put those 2 piles together. We have minus 12 root 35. And for my last, I have a 49 under the root sign, which has 2 identical factors of 7. There. And one last tidy up, 2 last tidy up. 4 times 5 is 20. Minus 12 root 35, which we can't simplify any further, and we have a 63. Lastly, we can put the whole numbers together. We have 83 take away 12 root 35. And by convention, because we want fractions to be particularly friendly in the denominator so that we can add fractions and so on, we don't like messes in the denominator. So we're going to rationalize the denominator, which means no radicals. So this is a problem. Doesn't matter what we have in the denominator as long as it's not a radical. So to get rid of root 3 in the bottom, I am going to multiply this rational by root 3 over root 3. In other words, I'm multiplying by 1, which doesn't change its value, but will change how it looks. On the top, I have 5 times root 3, which I can write as 5 root 3. On the bottom, I have root 3 times root 3, which is root 9, which is the same as the whole number 3. I have rationalized the denominator. For the second one, I have 6 root 2 over root 7, and it's the root that's the problem. So I'm going to multiply both top and bottom by root 7 over root 7, which doesn't change its value. I'm multiplying by 1. My top becomes 6. I can put both radicals together as a root 14. My bottom is root 7 times root 7, which is root 49, or the whole number 7. The last two are tricky. I don't like the radicals in the bottom. Root 3 plus root 5. In order to get rid of that, I am going to think about difference of squares. To square both the root 3 and the root 5 and to get rid of the radicals, I'm going to multiply top and bottom by, wait for it, root 3, take away root 5. As long as I do the same to the top, I haven't changed it, I just make it look different. I'm going to do a FOIL on the bottom. That will give me, first, root 3 times root 3 is root 9. This is my denominator. Outside is minus root 15. Inside is positive root 15. Interesting. And lasts are negative root 25. Top. I'm just going to write it as 2 bracket root 3 minus root 5. It's the bottom that I want to draw your attention to, that denominator. My root 9 is the whole number 3. Negative root 15 and positive root 15 cancel, and root of 25 is whole number 5. I'm going to end up with a negative 2 on the bottom, not a radical, which is exactly what I wanted. On the top, I'm just going to do distributive law, which would be 2 root 3 minus 2 root 5, because I can't add or subtract, unlike radicals. Final answer, 2 root 3 minus 2 root 5, which is far uglier than before, but the bottom is minus 2, which is lovely. By convention, we don't normally have a negative on the bottom. We often indicate the negative on the top. So I'm going to rewrite it like that, and I have rationalized the denominator. Last, 2 root 5 over root 6 minus root 2. I am multiplying by the conjugate, which is the opposite. Root 6 add root 2, and root 6 add root 2. That will allow me to do FOIL on the bottom and get rid of the radicals. On the top, it's 2 root 5 times root 6 plus root 2. I'll distributive law that in a moment. On the bottom, I am FOILing. Root 6 times root 6 is root 36, or whole number 6. Outside is root 12. Inside is negative root 12. And last is root 4, which is the same as whole number 2. 2 root 5 times root 6 is 2 root 30. Not much I can do with that. Plus 2 root 5 times root 2 is 2 root 10. Not much I can do with that. And the top is hideous. But it's the bottom that I'm concerned about. Root 12 and negative root 12 cancel. I am left with the whole number 6 and minus 2. I have 4. Probably it would be nicer if I were to simplify by factoring out a 2 from top to bottom. And I would be left with root 30 plus root 10 over 2. Page 167, numbers 1 to 12 and 15. There are some course note pages as well. It's the practice with radicals so that we can use them tomorrow to solve.